Molecules, Compounds, and Chemical Equations, Part 3. Today we're going to be looking at formula mass versus molecular mass, percent composition, calculating empirical formulas, and calculating molecular formulas. Formula mass refers to the mass of an ionic compound. So let's look at an example. Find the formula mass of calcium nitrate. Before I start to do any type of calculation, I've got to make sure that I have the correct formula for calcium nitrate. I know that calcium is Ca plus 2, and I know that nitrate is NO3 minus 1. And I'm going to cross these down to get the correct formula, which is CaNO3 2. So in this formula for calcium nitrate, we have calcium, we have nitrogen, and we have oxygen. When I look at this formula, I can say I have 1 calcium, and the atomic mass of calcium, roughly, is around 40. So 1 times 40 is 40. For nitrogen, because this 2 distributes through the parentheses, I have 2 nitrogens, and the atomic mass of nitrogen is 14. So 2 times 14 is 28. And finally, oxygen, 2 times 3, that gives me 6, and 6 times 16 will give me 96. So when I add these three things together, 40, 28, and 96, I get a grand total of 164 grams per 1 mole. And that is a little review of how to find the formula mass of a compound. Molecular mass is more specific. Molecular mass refers to the mass of a molecular compound. And remember, when we hear molecular, we think molecule. When we think of molecule, we think of nonmetals. And when we think of nonmetals, we think of covalent bonding. Just a little review. Find the molecular mass of sucrose, and the formula is given, C12H22O11. So what I'm going to do is I'm going to write down carbon, hydrogen, and oxygen. The formula tells me that I have 12 carbons. Each carbon has an atomic mass of 12. And 12 times 12 is 144. For the hydrogens, I have 22 hydrogens, and the atomic mass is 1, so that is 22. And finally, for oxygen, I have 11 oxygens in this formula. Atomic mass is 16, and that is going to equal 176. So when I add these three numbers together, I get a grand total of 342. So that is 342 grams per 1 mole for the molecular mass. Now let's talk about percent composition. The percentage by mass contributed by each element in a compound. So the percentage of each element is going to equal the number of atoms of that element times the atomic weight of that element divided by the formula weight of the compound times 100. Calculate the percentage of carbon, hydrogen, and oxygen in glucose. All right, so we're going to have carbon, hydrogen, and oxygen. We're going to figure out the percentage of each. So for carbon, I know that glucose has a formula of C6H12O6. So there are 6 carbon atoms in 1 molecule of glucose. The atomic mass of carbon is 12. And I just happen to know off the top of my head that the gram formula mass for this compound is 180. So again, that's the number of carbons, the atomic mass of an individual carbon divided by the total mass times 100. And when I work this out, I get roughly 40%. So 40% carbon. I'm going to do the same thing for hydrogen. I look at my formula. I have 12 hydrogens. Each hydrogen has an atomic mass of 1 divided by the total mass of 180 and multiply this entire thing by 100, and that will give me a percentage of around 6.67%. Finally, with oxygen, I have 6 oxygens in this compound. The atomic mass of oxygen is 16. I divide the whole thing by 180. And then again multiply by 100. And when I work this out, I get roughly 53.3%. And in a perfect world, when I add these all together, even though that's not going to be the case, I should get near 100%. Let's look at another example. Calculate the percentage of nitrogen by mass in calcium nitrate. We just worked with calcium nitrate in a previous problem, so we know that the formula for calcium nitrate is CaNO3 2, and we also know that the atomic mass of calcium nitrate is 164 grams per mole. So what we need to figure out is just the percentage of the nitrogen. So nitrogen equals, how many nitrogens in this compound? Well, there's 2. The atomic mass of nitrogen is 14. I'm going to divide everything by 164 and multiply it by 100. When I do this, my answer is 17.1% nitrogen. So here are 2 examples of how to do percent composition problems. Now let's go on to calculating empirical formulas. The empirical formula is the simplest whole number ratio of the atoms of each element in a compound and can be calculated from mass data. There is a simple method to follow, and we're going to go through the steps, and then I'm going to show you an example. If given percentages, which is sometimes the case, assume a sample of 100 grams and change the percentage sign into grams. Convert all mass numbers into moles. Find the smallest number of moles calculated in step 2 and divide all the results of the other calculations by that number. This is the most key step right here. The results should be in a convenient ratio and give the empirical formula. Note, it may be that the ratio includes a decimal or a fraction such as 0.5, 0.25, or 0.33, etc. If so, then multiply all numbers by 2, 4, or 3 as appropriate to remove the decimal. Don't just round up or down. You really need to think about your answers and try to convert everything into a whole number, and I'll show you an example of that. Calculate the empirical formula of the oxides of iron shown below. I am given percentages, so automatically what I'm going to do is just convert these percentages into grams. So 77.78 grams of Fe, 22.22 grams of oxygen. Okay, I have my masses. I'm going to go to step 2, and I'm going to convert each of these to moles. So grams of Fe needs to go on the bottom. 1 mole of Fe needs to go on the top, and the atomic mass of iron is 56. All right, so grams cancel grams. 77.78 times 1 divided by 56. Now, another key thing here. Don't worry about significant figures or anything at this point. Take it out a couple of decimal places. Don't round. So when I do this, I find that I have 1.389 moles of Fe. All right, that's good. Let's go on to oxygen. All right, multiplication sign in a line. Grams of oxygen on the bottom. 1 mole of oxygen on the top. 16 grams per 1 atom. Grams cancel grams. 22.22 times 1 divided by 16. I'm going to get 1.389 moles of oxygen. Well, that's interesting, because the third step now is to find the smallest number out of these 2 and divide the rest by that number. But hey, look, they're exactly the same. Amazing. So I'm going to divide both of these by 0.389. 1.389. And look, we get 1 and 1. And these 1s here represent our subscripts. So we are in a 1-to-1 ratio, which means that this would be Fe1O1. And we know that when we write chemical formulas, no positives, no negatives, no 1s. So this is just going to be FeO as our empirical formula. Let's look at a different example. 70% Fe, 30% oxygen. Let's start out by just assuming 100 grams. So 70 grams of Fe and 30 grams of oxygen. Multiplication sign in a line. Multiplication sign in a line. 1 mole of Fe, 56 grams of Fe. 1 mole of oxygen, 16 grams of oxygen. And let's do our work here. So grams cancels grams. 70 times 1 divided by 56 is going to give me 1.25 moles of Fe. And 30 times 1 divided by 16 is going to give me 1.87 moles of oxygen. All right, so now I'm on step 3. I need to look at these two numbers and say, okay, which one is smaller? And if you said 1.25, you're correct. So I'm going to divide this by itself, 1.25. I'm going to divide the bottom one by 1.25. So this is going to be worked out to be 1. And this is going to work out to be, oh no, 1.5. Now I can't just say to myself, I'll just round that up to 2 and it'll be fine. No, resist that. Instead, what you need to do is multiply these both by 2, because then you'll end up getting whole numbers for both of them. 1 times 2 gives me 2. 1.5 times 2 gives me 3. So then my formula here is going to be Fe2O3, because these numbers represent these subscripts. And it makes sense. If you unpack this formula right here, reverse crisscross it, it means that Fe will have a charge of +3 and oxygen will have a charge of -2, which we know are actual charges on the periodic table. So what we did here, by multiplying everything by 2, leads us to correct charges when we write our formula. So please, please, please take a moment, look at these answers, decide whether you need to multiply by something or you can round up or down. Let's look at another example. A hydrocarbon, a compound containing only hydrogen and carbon, has the following composition by mass: hydrogen 7.69% and carbon 92.31%. Calculate its empirical formula. So I'm going to start out with the 7.69, and again I'm going to assume 100%, therefore 100 grams. So grams of hydrogen and 92.31 grams of carbon. I'm going to convert each of these to moles. 1 mole of hydrogen, 1 gram of hydrogen. This one's nice and easy. So 7.69 moles of hydrogen. With the carbon, multiplication sign and a line. 12 grams of carbon on the bottom, 1 mole of carbon on the top. Cancel to make sure that my units are canceling. So 92.31 times 1 divided by 12 turns out to be, hey, 7.69 moles of carbon. They are both the same numbers, so I'm going to divide both of them by themselves. There is no smaller number here. So that means that this is going to be 1. This is going to be 1. So my correct formula here would be C1H1, and the ultimate formula would just be CH, because we assume the 1's there. So that is the empirical formula based on these percentages for this hydrocarbon. Calculating molecular formulas. We can obtain the molecular formula from the empirical formula if we are given the molecular weight or the molar mass of the empirical formula. The subscripts in the molecular formula of a substance are always a whole number multiple of the corresponding subscripts in its empirical formula. So whole number multiple is going to equal the molecular mass divided by the empirical formula mass. We need this. This needs to be given to us. We can calculate this if we have the empirical formula. The same compound as in the previous question has a molar mass of 78 grams per mole. What is the molecular formula of the compound? Okay, key thing right here. See this G mole -1? This is the same thing as grams per mole. It's just a fancier way of writing it, so don't get thrown off by that. In the previous problem that we did, we had an empirical formula of CH. And if we find the empirical mass of this, we know that carbon is 12, that hydrogen is 1, so this is going to be 13. In order to figure out the molecular formula, we have to have the molecular mass, which is 78, and divide it by the empirical mass, which we just figured out, which is 13. So 78 divided by 13 is 6. Now this 6 is what we're going to use to multiply all the subscripts in our empirical formula. So our empirical formula is C1H1 if we put the 1's in. We're going to put parentheses around the whole thing. We're going to put the 6 out here, and the 6 is going to be multiplied by the 1s. So that means the molecular formula of this compound is going to be C6H6, also known as benzene. Let's look at another example. The empirical formula of ascorbic acid is C3H4O3, and the molecular mass is 176 grams. What is the molecular formula? Okay, this is a very common type of problem. So we have ascorbic acid, which is C3H4O3. So I think about this and I say, all right, I need to get the empirical mass here. So I have 3 carbons times 12, that's going to be 36. I have 4 hydrogens times 1, that's going to be 4. I have 3 oxygens times 16, that's going to be 48. And if I add all these up, it's going to be 88 grams per mole for my empirical formula mass. They give me a molecular mass, and to figure out the molecular formula, I need to take the molecular mass, which is 176, over 88, which is my empirical mass. I divide that out, and in a perfect world, I should get a whole number. And in this case, I do. It's 2. So now what I want to do is I want to take my empirical formula, C3H4O3, and I want to multiply all those subscripts by 2. So when I do that, I'm going to get C6H8O6, and that is my molecular formula. And I know this is correct because technically I could divide everything here by 2 and get back to my empirical formula. So that's a little overview of how to find a molecular formula given an empirical formula and molecular mass. So what did you learn? We talked about the difference between formula mass and molecular mass. We talked about how to find percent composition of elements in a compound. We looked at calculating empirical formulas and calculating molecular formulas. Need more help? Feel free to contact me. Have a great day.